Hi you guys, so welcome back to my channel. Today we're going to go over one of my absolute favorite parts of pre-calculus, which is partial fraction decomposition. So you've learned how to add fractions. You spent a lot of time learning that in your K through 12 and beyond education, and now we're going to finally learn the process for the opposite of adding those fractions, which would be partial fraction decomposition. So my favorite application of where you're going to be doing PFD a lot is going to be in calculus, and it turns out that instead of having one big fraction, it helps to have a lot of different smaller fractions, which we'll clarify what that means in a second. But it turns out it's very useful to have them like that for integrating rational functions. So you will see this again in your math education. Okay, so let's take a look and just refresh ourselves on the process of adding fractions. So if I wanted to add together 1 over x plus 1 to the fraction 2 over x minus 2, what would have to be the case is that we'd have to have a common denominator. So x plus 1 and x minus 2 are obviously different denominators. What we would want to get is the lowest common denominator, which can be found by multiplying each fraction by the missing factor. But when you adjust a ratio, you have to multiply the numerator and the denominator by the same thing so that you don't actually change the fraction. So when we multiply 1 over x plus 1 by x minus 2 over x minus 2, we get x minus 2 on top, and the bottom becomes x minus 2 times x plus 1. Now don't combine those because that's actually going to be not super helpful for what we're trying to do. And adjusting our second fraction, we multiply numerator and denominator by x plus 1 over x plus 1. So the numerator becomes 2 times x, 2x, 2 times 1 plus 2. And the denominator is, of course, x minus 2 times x plus 1. Now that we have the same denominator for both fractions, we can go ahead and add. So adding our like terms, we have x plus 2x gives me 3x, and we have negative 2 plus positive 2 gives me 0. So we have our fraction, 3x over x minus 2 times x plus 1. So if we look at our two versions of this rational expression, let me highlight them. We have our starting version, and we have our final version. Okay, so the process that we've worked on previously has been adding. That's what we just did. Decomposition is what we're going to learn in a second, and that's going to be the process where we go from our pink 3x over x minus 2 times x plus 1 back in time to our simpler addition of two fractions. So what makes it simpler is that our original expression had only one factor in the denominator instead of having a product of factors in the denominator. So that's going to be our goal. Let's take a look at how we're going to do that. So how to do partial fraction decomposition. Some of it is going to be a little bit of pattern recognition. So the first thing we're going to do is we're going to need to have our denominator factored. And if we look back up at that previous example, why would having the denominator factored be important? Is because each of your fractions has one of those factors as a denominator. Turns out that's always going to be the case. Okay, so we're going to have our denominator factored. The numerator does not matter. And then we're going to look at the denominator and we're going to identify how many terms our fraction expression that we're going to end with will have. So our rules for our pattern setup is going to be, we're going to be looking for the number of fractions for each factor. And this is a factor over R, so we're not doing this for complex factorization over C. So the number of fractions for each factor is the multiplicity. Okay, and let's look back up at our previous example. So notice the multiplicity for x minus 2 was multiplicity 1, and so there was one x minus 2 fraction. And the multiplicity for x plus 1 was 1, so there was only one fraction with an x plus 1. And then we need to know a little bit. We're not going to know initially the exact values for the numerator, but we will be able to know at least what kinds of numerators we are looking for. So the types of factor are going to be either you're going to have linear, or quadratic. And the quadratic is obviously going to be something that is irreducible, so you can't factor it over R. So again, we're going to see that our skills with factoring are very important here because we need to know whether a quadratic does or does not factor over R. If it does factor over R, we must do so at the very beginning, or we're not going to have the right number of terms and the right pattern for the numerators. So it's important to know going in whether you factored something completely or whether you have not. So the two types of factors when we break these things up are going to be linear or quadratic, and the type of numerator that you're going to have for the linear factors is going to be a constant. And we tend to use capital letters A, B, C, D, E, F, so on. We start at the beginning of the alphabet, so just a constant. And the type of numerator for a quadratic would be something like BX plus C, a linear. Okay, so we're going to be very careful to notice that the type of information that goes in the numerator is entirely dependent on what is being raised to our multiplicity. So like for instance, if we had x minus 2 quantity squared, if that was our kind of factorization versus something like x squared plus 4, let's move this over here to give us a little more room to look at this. We've got it factored completely. We can't break the x squared plus 4 up anymore. We don't really need to know the numerator to do the setup for this. But I know that my setup is going to be, I'm going to have two terms coming from the x minus 2. And I'm going to be counting up to them. So x minus 2 plus x minus 2 squared. Okay, what goes in the numerator for those is going to be constants. Make sure you choose different letters because they might be different numbers. And notice the thing about the quadratic versus linear, notice that what's inside being raised to the multiplicity of 2, x minus 2, that's linear. So it's still getting a constant in the numerator. Okay, and then for our second factor, x squared plus 4, its multiplicity is 1. Multiplicity is 1 because it's only being raised to the first power. But the numerator should be linear cx plus d. Okay, so hopefully that example shows us the pattern of what we're going for. And what we get in the end is we're going to get 4 unknowns here. We got A, B, C, and D, and those are the things we're going to be solving for. So how are we going to do it? We're going to have a system of equations that comes out from some algebra, and we're going to use our system of equation to solve and remind ourselves we are not solving for x. We are rather solving for A, B, C, D, so on. Because if we think about what we're doing, we're not solving an equation here. We are trying to change the format of an expression. So when we solve these, just be careful to think about that. It's not autopilot always we look for what x is. We couldn't even figure it out if we wanted to. So let's jump in and take a look at a specific example here. But we're going to pretend like we don't know how this one's going to work out. We're just going to see how it goes. So my pattern, I'm completely factored. My denominator is completely factored. If factoring is giving you a challenge, you're going to want to look back at some of my previous videos on factoring techniques and how to do this over R versus over C. So it looks like my format is going to be 1 fraction over x minus 2. 1 fraction is going to be over x plus 1. And it should be constant A plus B. And our equation that we're setting up is our original 3x over x minus 2 times x plus 1. Okay, so now what I'm going to do is I have my setup. I need to try and get to some sort of equation that allows us to relate A and B to things that we know. So how we're going to do that is we're going to cancel fractions. We're going to multiply to cancel fractions. So what we're going to multiply by is the denominator on the left, which is the lowest common denominator for all fractions. And note that we're multiplying by a whole number. We're multiplying both sides of the equation by this. Our left side's going to be a little bit cramped here, but that's okay. We don't really need too much of it. So our fractions are going to get canceled. We'll be left with 3x on the left. We'll be left with a times x plus 1. Okay, so let's look at why that canceled that way. The x minus 2 on the denominator here canceled with this x minus 2, and the x plus 1 is still left behind. Similarly, for our next factor, we're going to get b times x minus 2 because our x plus 1 canceled top and bottom. Okay, so coming down, we have a little bit easier equation that we're looking at right now. I'm going to bring my a and b in by distributing, because what I want to look at is looking at coefficients and matching powers of x's on both sides. So if I have an equation that has polynomials on both sides, the coefficients must match. Okay, so I'm going to highlight the different powers of x. Okay, so I only see x to the first on the left. I'm going to highlight all the terms that also have an x to the first. Okay, I'm going to do in a different color. There is no constant, so we'll just highlight that blank space on the left, and it's going to be 0. So there's none. But then we have these constants. So now I have two equations that are just going to be formed here, because I know that on the left, if I have 3 x's, and I'm going to actually write this in the way we're going to have to put it into our calculator. So pardon me switching our sides on us, but this is how it's going to enter into a calculator. So on the left, we had 3 total x's, and on the right, we had a plus b total x's. And it must be the case that when you add ax plus bx, if it's going to be equal to the left, there should be 3 total. So we've got our first equation, and that is that a plus b must actually equal 3. We've matched the coefficients on the x term. Okay, so now we'll do the same thing for our constants. Okay, so on the left, we had 0 for our constant. And on the right, we had a positive, negative 2b. So lining up my a's, because I now have a system of equations. And as we have just learned system of equations not too long ago, you guys might remember that yes, we can definitely solve these by hand. That's 100% okay if you feel like you want to do that. But it's going to be depending on your teacher as to whether they have any preferences. At this point, I do not mind my students using graphing calculators to help speed along this computation, as I feel that we've already practiced systems of equations. But that's my personal preference for pre-calculus, and it's definitely not a universal philosophy. So just make sure you check in with your professor on that. So what's going to go into our graphing calculator is we're going to solve the system a plus b equals 3 and a minus 2b equals 0. You guys might remember what's going to go into the calculator here is 1, 1, 3, 1, negative 2, 0. And then we use our TI or what have you to put that into reduced row echelon form, and you'll get your solution. So moving us over to the calculator, what do we end up getting from that is we end up getting that our a is 2 and our b is 1. So then for our final step, we're just going to make sure to write the actual answer that we were trying to find. We were trying to find the partial fraction decomposition. So the 2 is what goes over the x plus 1, and the 1 is what goes over the x minus 2. So there's our partial fraction decomposition. Okay, so one thing to make sure to pay attention to is write the number that goes over the appropriate factor. So it's easy to get it mixed up here, but as long as everyone's writing down their answer and they're matching their variables with what they got, it doesn't matter if you chose the letter A or the letter B to go over the x minus 2x plus 1, because in the end, we're all going to get the same answer as each other. Okay, so let's move on to another example. This one's a bigger one. I wanted to choose one that would give us a little bit more challenge. So paying attention to our denominator, is it factored? X minus 2 quantity squared, yes, that's factored. 2x squared plus 1, that is a quadratic. It is irreducible over r. And if you're not sure about that, you can always do a discriminant, and that'll let you know that, hey, this quadratic doesn't factor anymore. So if we come and do our setup, let's be careful to count out our factors. We're going to get 2 factors for the x minus 2. And we're going to get 1 factor for the 2x squared plus 1. And what goes in the numerator would be constants for the x minus 2 factors and a linear for the 2x squared plus 1. Making sure to choose different letters for every single term. And then let's set our equation up on the left-hand side with the original. We have 3x cubed minus 10x squared plus 12x plus 1 over x minus 2 squared over 2x squared plus 1 as well. Okay, so what are we going to multiply both sides by? We're going to multiply both sides by the lowest common denominator, which is that fraction on the left. So we're going to multiply by 2x squared plus 1, x minus 2 quantity squared all over 1, left and right. Okay, so if you feel like your fractions are not canceling here, something's going wrong. That is the whole point of what we're doing, is we're trying to cancel fractions. So if you feel like your fractions aren't canceling, I'm going to make a prediction that you have not identified the correct setup for your partial fractions. That means that I think probably what you've done is you didn't quite get these terms correct, and so things are feeling like they're not canceling. That's not the only, that's not going to always catch your mistake, is just that it cancels. Like, you might make a mistake otherwise with your setup, so it is very important to keep in mind the rules and have those very clearly memorized, because it will feel like you've done this right, possibly, even if there was something wrong with your setup. Okay, so let's look at what happens when we multiply our fractions through. So on the first term, on the left-hand side, the fractions are going to cancel. 3x cubed minus 10x squared plus 12x plus 1. And on the right-hand side, a is going to be multiplied by just one of the x minus 2 factors, because one of them will cancel. And then it will be multiplied by 2x squared plus 1. And we'll need to do a little bit of work to figure out what that is. For the second term, both of the x minus 2 squareds are going to cancel, and it'll leave us with a 2x squared plus 1 times the b. And then for our third term, the 2x squared plus 1 will cancel, and we'll have cx plus d times x minus 2 squared. Okay, so now at this point, what we want to do is completely expand out our left and right-hand equations. And some people are a little bit more visual and prefer a little bit more writing. Some people can get away with doing this in their mind and not really actually having to do the full expansion. But in the effort of just getting an explanation that's going to make sense to the most amount of people, I'm going to show you guys more work in this step than what I would necessarily need to see from you. But I think it will help some students who struggle a little bit more with this. Okay, so let's start with our FOIL. We have a times 2x cubed plus x minus 4x squared minus 2. First, outside, inside, last. For our second, we have, this one's easy. We can just do this one right away. 2bx squared plus b. And then we have a step of foiling for our third term, cx plus d times x squared minus 4x plus 4. I did the FOIL there in my head. And it looks like we're going to have to do one more step of expansion here in our third term. We actually have to FOIL out what that's going to be as well. So we'll get cx cubed minus 4cx squared plus 4cx plus dx squared minus 4dx. Really want to fit this on one line for us so that we can see it. And then plus 4d. Okay, so we've got that one all multiplied out, and we'll multiply the a in to all terms. We have 2ax cubed plus ax minus 4ax squared minus 2a plus 2bx squared plus b. Whew, okay. Perseverance got us there. So let's copy down our equation here. Remind ourselves what we're going to be setting equal. We're now at this part where we're going to match coefficients. So I'm going to go ahead and highlight. We're going to match every power of x. So we'll start with our x cubed. Then we'll go x squared, x, and constant. And we notice there are 4 equations, and we also have 4 unknowns. That should always be matching. Okay, so first we're going to do our x cubed. Let's get a little color coding going here. So I'll highlight the cubic terms in yellow. Got 3x cubed on the left, 2ax cubed, cx cubed, and it looks like that is it. Okay, so on the left, again, I'm switching the sides right now because I'm getting us ready to put it in the calculator. So on the left we had 3, and on the right we had a, leaving some space for a b to go for some other equations. So a plus c of them. And then next we have our x squared. It looks like there's negative 10 on the left, negative 4a plus 2b, negative 4c plus d. So we have negative 10. We have negative 4a plus 2b minus 4c plus d. And then for our x term, there's positive 12 on the left, positive a, positive 4c, negative 4d. So we have 12. There's a plus 4c minus 4d. And then lastly, we're at our constant. We have positive 1 on the left, negative 2a plus b plus 4d on the right. So on the left, we got 1. On the right, we have negative 2a plus b plus 4d. It took a lot of care to try and line things up in columns. So when we go to put this in our calculator, we're going to have 1, starting with our top equation, 1, 0, 1, 0, 3. Remind yourself that we're missing both the b and the d, so that's why we had to put those zeros there. Okay, next we have negative 4a. Don't need the letters in there, huh? Negative 4, 2, negative 4, 1, negative 10. For the next, we have 1, 0, 4, negative 4, 12. And for the last, we have negative 2, 1, 0, 4, 1. Okay, this is where we really in these problems want to be careful going each step, checking to make sure we didn't make any small mistake, because as you guys have learned at this point, with solving systems, organization, diligence, and proceeding with caution is the 3 things that are going to really make your process organized and complete and less likely to have mistakes in it. So I'm just going to look one more time for our top equation, 1a, 0b, 1c, 0d, 3. Negative 4a, 2b, negative 4c, 1d, negative 10. Third equation, 1a, 0b, 4c, negative 4d, positive 12. And for our last equation, negative 2a, positive b, 0c, 4d, 1. Okay, whew, looks like we made it to the end. So let's go ahead and hop on over to the calculator, and we'll put this information in. And from our calculator, we see that we get the matrix put into RREF. You'll be getting from your calculator that you have 1, 0, 0, 0, 0. And for the second row, you get 0, 1, 0, 0, 1. For the third row, you'll get 0, 0, 1, 0, 3. And for the last row, you'll get 0, 0, 0, 1, 0. Okay. So at this point, I'm assuming that you've went ahead and watched my videos on solving systems that involved using technology to interpret what this gets. But a quick little refresher of that is that when your matrix puts this into reduced row echelon form, each column corresponds to where the variables were. So this was our A column, B column, C column, D column, and constant. And the ones represent saying that 1A equals 0. So this says that A equals 0, B equals 1, C equals 3, D equals 0. Okay, so now let's look back to our original starting setup. So our starting setup is that there is no x minus 2 term. Okay, that's fine. That can definitely happen. Okay, and then for our C, we get 3. For our D, we get 0. So we get that this fraction should be 1 over x minus 2 quantity squared plus 3x over 2x squared plus 1. Okay, that's our final answer. But, so you guys know, you can actually check yourself on these. And you know how to check yourself. We've seen it already. The opposite of PFD is adding. So if you've done this process correctly, you can actually do the check for yourself to verify, did I do this properly? So you can come and try and add your fractions back together, and you should get the original fraction back. So when I multiply this through, I'll show you the check. You'd get 2x squared plus 1 over x minus 2 quantity squared times 2x squared plus 1 for the first fraction, added to 3x times x minus 2 quantity squared, which is x squared minus 4x plus 4 over 2x squared plus 1 x minus 2 quantity squared. And combining my numerators, I get 3x cubed, and then minus 12x squared plus 12x. So adding the 2x squared to the negative 12x squared, I get minus 10x squared. And then adding the 12x, it looks like there is no x term for our first fraction. So it'll just be 12x, and then I have a constant plus 1. Okay, so I'm going to go and look at my original problem. And is this equal to the original? 3x cubed minus 10x squared plus 12x plus 1. So I'm looking back at the original, and they do, in fact, match. So yay, we did this process correctly. Okay, good job making it through this, you guys. So a couple summarizing thoughts on this whole process is that partial fractions is one of those processes where I can definitely see where a student might feel like it is very tedious. I can see why you might be thinking that. However, what I will say about it is it's one of those things where it is what it is. We have to do it in order to perform calculus on certain kinds of functions that pop up all the time. So this process definitely is going to be one where you will continue to see it in your math journey. And with that thought in mind, just kind of take it as, at first, maybe a necessary evil that hopefully kind of grows on you as you become more familiar with the process. Another thing for my students, again, I can't speak for all pre-calculus instructors, but for my students, I personally do not need to see you demonstrate a check every single time for any sort of point value. My preference is for my students to only do the check if they have time for themselves at the end of an exam so that they can feel confident that they did the correct thing. If they were at home just wanting to check themselves on homework, then that's great. A great way to do that. Okay, so hopefully this video helped teach you partial fractions decomposition, and I will see you guys next time.